In this tutorial, we will be discussing the nature of light and the electromagnetic spectrum. Alright, so back in 1937, there was a huge explosion with the Hindenburg, where a third of their passengers died. It turns out that hydrogen gas was ignited, and the hydrogen gas was what was so light that allowed it to lift up into the air. And hydrogen is actually extremely explosive. And so as it started to land, something ignited and it caught on fire. Alright, so what makes that hydrogen gas so very reactive? Nowadays, modern balloons use helium, which is not as reactive. In fact, it's inert. The nucleus of the helium atom has 2 protons, and thus the atom itself has 2 electrons. And is extremely stable. So here we're going to learn about the inertness of helium and the reactivity of the other elements. So what is it about helium atoms that make helium gas inert? And why is hydrogen so reactive? Hydrogen itself doesn't even exist by itself. It exists as a diatomic element. So hydrogen atoms are so reactive that they react with each other to form hydrogen molecules. So what is it about hydrogen that makes them so reactive? The answer is the electrons. And so the question is, how does that relate to the rest of the periodic table? The reactivity exhibited by hydrogen is also seen in other group 1A elements, such as lithium and sodium. The inertness, what not to react, is the same as like neon and argon and other noble gases. And it all has to do with the placement of the electrons around the nucleus. Mendeleev, long time ago, put the modern periodic table together using the periodic law. And it basically sums up 2 different observations. One is if you arrange the elements in an increasing atomic number. Notice atomic number, not atomic mass. So when we look at these the bigger numbers that are not whole, those are not what's being lined up. It's the numbers on the top, the whole numbers. Those are the atomic number. So when you do that, certain properties recur. So that means all of these will react similarly. All of these will react similarly. All of these will react similarly. Models and theories help explain the observed behavior of groups such as the group 1 metals and the noble gases. So if we look at the electrons a little bit closer, we realize 2 important models. That's what we're going to be discussing, the Bohr model and the quantum mechanical model. They propose the explanations of the inertness of helium and the reactivity of hydrogen and the periodic law. These models explain how electrons exist in atoms and how the electrons affect the chemical and physical properties of elements. So here we have Niels Bohr and Erwin Schroedinger, along with Albert Einstein, played a role in the development of the quantum mechanical model. Yet they were kind of confused by the fact that the electron had reacted in 2 different ways, and they call that the duality of the electron. Dual being 2, they act as waves and they act as particles. So they act as a wave particle with light electromagnetic radiation. The interaction of light with atoms helped shape the scientists' models of the atom. Light is a form of electromagnetic radiation, which we'll be talking later in this video. Light is a type of energy that travels at a constant speed of 3 × 10⁸ meters per second, and the properties of both wave and particles. So it behaves like waves. Over here, when a water surface is disturbed, waves are generated. They are then radiate outwards from that site. The wave carries energy as it moves through the water. Just as with the light here, there's an energy that associates with the wave. So right now we're just going to dissect a wave. Here we have lambda. It's from two equal parts. So it could be two troughs, two crests. It's the distance from one part of the wave to the other. Here they have it specifically to the crests. The crest is the top. Just to clarify, the crest is the top, the trough is the bottom. And the lambda is the wavelength between two crests. So white light is produced by the sun or a light bulb. Contains a spectrum of wavelengths and therefore a spectrum of color. We see the colors red, orange, green, blue, indigo, and violet in the rainbow, or when white light passes through a prism, because it breaks up those different wavelengths. Red light, with a wavelength of 750 nanometers, has the longest wavelength of visible light, while violet, with a wavelength of 400 nanometers, has the shortest wavelength of visible light. The presence of color in white light is responsible for the colors that we see in our everyday vision. A mnemonic device for this is RoygBIV. It stands for red, orange, yellow, green, blue, indigo, and violet. Red, orange, yellow, green, blue, indigo, violet. RoygBIV. So light separates into these colors when it passes through a prism or a rainbow. Here's an example of how we see the light. This red shirt appears red because it reflects the red light. So when we look at the different wavelengths, it's reflecting this wavelength right here. But it absorbs all the other wavelengths. So what we see is what's reflected. So we learned about lambda. Lambda is the distance between 2 points. So it's the wavelength. Frequency is abbreviated with a nu. It's basically a V that has like a little curve on it. And that's another Greek letter. It's defined as the number of cycles or crests that passes through a stationary point in 1 second. So if the wavelength is moving, and we're marking it right here, every time the crest goes through that point, that marks another part of the hertz. That marks the frequency. Wavelength and frequency are inversely related. The shorter the wavelength, the higher the frequency. So notice as we go from left to right, the wavelengths get smaller, 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 yet but the energy gets higher and the frequency gets higher. Alright, so the light can be viewed as a stream of particles. It can also be called a photon. So remember the duality of light. We just saw it as a wave. Now we're looking at it as particles. So it has both the wave and the particle, which is the photon. We can think of a photon as a single packet of light energy. The amount of energy carried in the packet depends on the wavelength of the light. The shorter the wavelength, the greater the energy, which is what we saw here. Light waves carry more energy if the crests are closer together because the shorter the wavelength. Violet light, which has a shorter wavelength, carries more energy per photon than red light, which has a longer wavelength. Alright, so let's summarize what we've learned so far. Electromagnetic radiation is the form of energy that travels through space at a constant speed, at 3.0 times 10 to the 8th meters per second, and can exhibit wave-like and particle-like properties. The wavelength of electromagnetic radiation determines the amount of energy carried by one of its photons. The shorter the wavelength, the greater the energy of each photon. The frequency and energy of electromagnetic radiation are inversely related to its wavelength. So frequency and energy. So as the wavelength gets smaller, or it goes down, as the wavelength gets smaller, the frequency and the energy will get bigger. So let's take a minute to look at the electromagnetic spectrum itself. The entire electromagnetic spectrum, with short wavelength, high frequency radiation on the right hand side, and long wavelength and low frequency on the left. The visible light is a very small sliver in the middle. So the shortest wavelength here are the gamma rays. Gamma rays are produced by the sun, the stars, and by certain unstable atomic nuclei on Earth. Excessive exposure to gamma rays is dangerous because of the high energy of gamma ray photons that can damage biological molecules. Next we have X-rays. They have longer wavelengths and lower energy than gamma rays, and they're familiar to us through medical use. X-rays pass through the many substances that block visible light and are used to image internal bones and organs. Like gamma ray photons, X-ray photons carry enough energy to damage biological molecules. While several yearly exposures to X-rays are relatively harmless, excessive exposure to X-rays increase cancer risk. Next, we have UV light. Between X-rays and visible light is the electromagnetic spectrum is the UV, ultraviolet light. Familiar to us as the component of sunlight that produces sunburns or suntans. While not as energetic as the gamma or X-ray photons, ultraviolet photons still carry enough energy to damage biological molecules, which is why we get burned or tanned. Excessive exposure to ultraviolet light increases risk of skin cancer, cataracts, and causes premature wrinkling of the skin. Next, we have visible light, which is probably what you're most familiar with. It ranges from shorter wavelengths such as violet to longer ones such as red. Photons of visible light that do not damage biological molecules. Photons of visible light do cause molecules in our eyes to rearrange, which send signals to our brains and result in vision. Now, just as a little helpful hint on how to know where the colors line up. You see ultraviolet right here, while on the far right hand side we have violet. The shortest wavelength is violet, and then even shorter is ultraviolet. The longest wavelength is red, while right below it is infrared. So that might help you with memorizing the electromagnetic spectrum. Alright, so infrared is next, with even longer wavelengths than visible light. The heat you feel when you place your hand near a hot object is infrared light. All warm objects, including human bodies, emit infrared light. While infrared light is invisible to our eyes, infrared sensors can detect it and are often used in night vision technology to see in the dark. In the infrared region of the spectrum, warm objects such as human bodies glow much as a light bulb glows with the visible region of the spectrum. So here we have an example of an infrared photograph. So over here on the right hand side, you can see the warmest areas giving off the most energy. So therefore, that's what's detected in these cameras. Alright, next we have microwaves. It has longer wavelengths and used for radar and microwave ovens. Microwave light has longer wavelengths and therefore lower energy per photon than visible or infrared light. Microwave light is efficiently absorbed by water and can heat substances that contain water. Substances that contain water, such as food, are warmed by a radiation of a microwave oven, but substances that do not contain water, such as a plate, are not. Some types of dishes contain substances that absorb microwave radiation, but most do not. And finally, we have radio waves. These are the longest wavelengths, which means that they also have the lowest amount of energy. They transmit signals for AM and FM radio, cellular phones, television, and other forms of communication. They're not harmful to us whatsoever because they're in such low energy. And that gives you an overview of light as both a wave and a photon.